Welcome to the lesson on 12.2, Geometric Sequences. The central question is, how can you define a geometric sequence algebraically? Before we start to define algebraically, let's think about a tree, right? How a tree trunk is over here, and at the end of that, we will draw a branch, two branches. And then following that, in the two branches, we'll draw two branches. And then we continue in that fashion. This is one of the examples of a mathematical object called fractal tree, right? So what we have is a stage 0, 1, 2, and 3 are shown, right? In stage 2 over here, guys, right here, previous to 2, there are 4 new branches because we double at the end of the 2 branches that with those existing, right? And then the length, we drew it like half of the previous length, will be 1/4 of the unit length of the previous, right? But let's just focus on the number of branches here. For stage 3, which is this one, there are 8 new ones. So the total of, there's 8, and there is 4, and there is 2. What that means is that stage afterwards, because there were 8 of them over here, we're doubling each time, so there has to be a total of 16 branches for stage 5. And then stage after that will be 32. Thus, each stage we add twice, 2 times the one that we had before, right? You could visually see that over here. Well, let's try to make a table out of it, and then from here we could write it geometrically. So if we had 2 here, we double the one before. At stage 2, we got a total of 4 branches, and what do we do after that, guys? We multiply by 4, right? And then after that, we multiply by 8, 16, and 32, thereby getting 2, 8, 16, 32, 64 branches respectively. Is there a way we could draw this thing? All right, the first one is 2 to the 0. Second one is 2 to the first, 2 to the second, and that is 2 to the third, fourth, fifth, and 2 to the sixth. For this particular one, I think we have a pattern going on, right? So for D, we could do 2 branches on each branch. So what does that mean? And 4. How many branches are there relative to stage 3? It's twice the one before. How about 5? It's the twice before that, and so on and so forth. So the ith branch is twice the one before that, which is I minus 1. The subscript just tells you which stage it is in. It's just a small notation for that, right? Now, let's think about how to write this more explicitly. How many are there on a certain stage, right? Like S being the number of stages. We just sort of go take a look back over here, guys. We notice that the number of branches as a power, that the power matches the stage, does it not? Right. The stage is S equal to 0, 1, 2, 3, 4. If in stage 5, the number of branches is 2 to the 5th. So the way we write it is 2 to the 5th. Sorry, 2 to the S. So number of stage matches the exponent right there. So 2 to the S in this particular case. All right, guys. We see more examples over here, but we could do the rest of this in class. We have enough to move on, so let's skip ahead to the example that we're going to be working on. All right, guys. So we're trying to define what a ratio is, right? So in geometric sequence, we had noticed it went something like this. We had 1, 2, 4, 6, 8, 16, 32, 64. What we noticed was that we multiply from the first to second by a fixed number, which is 2. and then we just kept multiplying over and over again. That is a very definition of a geometric sequence. The next term increases or decreases by a common fraction, right? That ratio is constant, right? That 2 does not change. And that ratio is called common ratio. And in the explicit form of this, we kind of did it out already. It was the first term, because that term we can't control, can be different for each sequence, times the ratio times n, or ar to the n minus 1. That really depends on how you label things. If the first number, we label them as a 0, 1, 2, 3, and so on and so forth, we go with ar to the n. If the first count is 1, 2, 3, 4, we go with ar to the n minus 1, kind of like what we did in the past. So once again, a is the initial value, r is the common ratio. Now, in a recursive form, we basically multiply the previous one. F of n is whatever the previous term is, which is expressed as f of n minus 1 times the common ratio of r. And we define the first term as either f of 0 is equal to a, or f of 1 is equal to a, depending on where we start the count, either with a 0 or 1. Okay, let's do an example here. So in this particular case, what is my common ratio? Well, to go from 3 to 6, what do we have to do? We doubled, right? Another way to express that is we divide 6 by 3. And 12 by 6, 24 by 12, and so on and so forth. And we find that that is equal to 2. So you double each time to get to the next term. So you do that by whatever term you have, divided by the previous term is common ratio. Looking at this list, the initial value is 3. We usually denote that with a. So the explicit formula is f of n is 3 times 2 to the n, where r is the common ratio. And in this case, because n started with the 0, we write down n. If it started with 1, we write n minus 1. If you have a problem with this, we'll try to clarify that in class. In the recursive form, as we mentioned before, it's a previous term times the common ratio, which is 2. And in this case, n has to be greater than or equal to 1. We have to denote that f of 0 is 3. So by writing this, we say that the first term, we start counting with a 0 count, 0. And in this case, it's 3. All right, so let's try one more example. Instead of doing the a this time, let's try b, shall we? All right, guys, given this definition, fill out the table. Okay, let's examine this. So f of n is the current term, and f of n minus 1 is the previous term. And to get the current term, we multiply the previous term by half. Got it. Okay, then what's my first term? In this case, 0th count. F of 0 is 16, so plug it in there. To get the next one, I multiply by half, and then continue to do so, which yields 4, 2, 1, and a half. And the question is asking you to plot this, right? So right now, we're going from expressing this as algebraically to using algebraic expression. We're deriving the table and also physically seeing what it looks like, right? All right, so first one is at 0, 16, right up there. The next one is half of that amount, which is 8. Notice that it dropped the height in half. And the next one drops, I believe, should be around here, right? To 16, and we will fill the rest right there. And it looks like it's dropping pretty fast, isn't it? And each one is half the height of the previous. And I think half of that would be quarter and eighth and so on and so forth. Towards the end, it will be very, very close to 0. Right? Okay, guys, I think this is enough. Have a good night.